A new distribution we're going to be looking at is what we call the chi-square distribution. But for the first homework, I just want you to learn how to use the table. We're going to find critical values for the chi-square distribution. Now, on your PDFs, on besides the notes, I also gave you guys this table here. I gave it to you guys in both pages. Here I'm displaying both pages at once. So yours, you guys see one page, and then the second page, here I'm displaying both. But I want us to know how to use the critical values table for chi-square. Now, what I'm going to be doing is my chi-squared, the way we're going to read my chi-squared, it looks like an x squared. Now, at the bottom of the chi-squared, at the bottom right here, that's where I'm going to put my alpha. So when I come over and then ask you guys for values, I'm going to ask you guys to check for a specific alpha. So here at the top, you guys can see, you guys have to find the corresponding alpha. There's some high values on the top, on the first page. There's some low values of alpha on the second page. Remember what alpha is. So when we're looking at a distribution, sometimes I ask you guys for confidence intervals. Sounds familiar that we've done this before. So I just want to know, let's say I have a distribution. This have to be normal distribution, but everything in between my parentheses that I did here, that's how confident I want you to be. Sometimes I ask you guys to be 90% confident, 95% confident. So you guys, when we talk about confidence intervals and I use percentages, that's how confident I want you guys to be. However, there's some left here, right? If I said I want you to be 95% confident on your answer, 95% sure, 95% confident. So there's a remainder. In that case will be 5%. That is what we call our alpha. So when I come and say we're going to check for our alpha to be 0.1, that's basically 10%, right? When we think about a decimal, 0.1 is 10%. So if I say we're going to check for alpha to be 0.1, that means I want you to be 90% sure on your answer. Okay, so now that we know where our alpha is, so we see that our tables, they have some alphas on the corresponding alpha that we have, and there's some degrees of freedom. So let's take a look at our notes. We have to find an alpha value and a degrees of freedom value. So for the first question, find the rejection region for a one-dimensional chi-square test of a null hypothesis concerning various samples. When I mean various, I mean like sample 1, like P1, P2, P3, all the way to Pk. So that means various samples. But then I see if k is equal to 15. So basically, I'm saying if there are 15 samples and an alpha of 0.05, so we're going to be 95% sure on our answer, the rejection region of a chi-square is greater than, and I see some space there, so I'm going to have to fill out the value. So let's see. I know my table had alpha, so let me identify the value of alpha. My value of alpha in this case is 0.05. And I remember the table that there was something about degrees of freedom. Let me abbreviate this with DF, degrees of freedom. Now I see a value of 15. K is equal to 15. Now my degrees of freedom are not going to be 15. My degrees of freedom is going to be one less than that. So basically our K value minus 1, in our case, 14. My degrees of freedom is 14 because K is 15, so 15 minus 1. Always subtract 1. Okay, so I'm looking for the rejection region when my alpha is 0.05 and my degrees of freedom is 14. So let me take a look at our table. Let me find the corresponding alpha. I see it here. You guys see the value of alpha there, 0.050. So 0.050. It's the same thing as 0.05. 0.050. So there's my corresponding alpha. My degrees of freedom was 14. So I see my 14 here. And these two meet at this value, 23.6848. I had to round it to 4 decimal places, so that's great. I have my answer in 4 decimal places. So let me go back to my notes here, and I'm going to complete my answer here. The rejection region is chi-squared greater than 23.6848. That's it. That's all I got to do. Now let's take a look at my second question. Find the rejection region for a test of independence of two classifications where the contingency table contains R many rows and C many columns. So there's some rows, there's some columns. So we're looking at a table. Now my alpha is going to be 0.05 this time. There's going to be 4 rows. So R is equal to 4. So there's 4 rows and 5 columns. Okay. So I know I need an alpha value. So I have my alpha value. Alpha is going to be 0.05. More than likely, the way I'm going to see it on my table, I'm going to do 0.050. Mathematically speaking, 0.05 or 0.050 is the same thing. Now, my degrees of freedom. I know I have to subtract 1. Like on the first example, I had a k value, so just 1k minus 1. However, now I have 2 values, rows and columns. Whatever the value of rows is, I'm going to subtract 1. Whatever the value of column is, I'm going to subtract 1. Notice how I put each of them in parentheses. And the reason why is because I subtract 1 from each value, and then I multiply the two values. So that's going to be my degrees of freedom. In this case, because there are 4 rows, so my first number is going to be a 3. Right? 4 minus 1. My second value, because there are 5 columns, so my second value is going to be 4. Right? I always subtract 1. Now, when I multiply these two values, 3 times 4 is 12. So I'm going to look at my table. My alpha is going to be 0.050. My degrees of freedom is going to be 12. And then it says round to 4 decimal places as needed. Okay, let me take a look at my chart. By coincidence, it gave us the same alpha value. So we have it. Our degrees of freedom is 12 this time. So I see 12 here. Now these two values meet right here. So 21.0261. Okay, let me come back to our notes here. Chi-squared is greater than 21.0261. Again, the first assignment is going to be pretty simple. Want you guys to get familiarized with the table. Later on, we're going to do some studies, and that's going to be my critical value. So that's why we call this finding critical values for chi-square distribution. Okay. So again, it's easy, but I want you guys to know how to use this table because we're going to be using it later.